Okay, thank you very much for inviting me to give a talk here. It's a big honor for me. And the title of the talk, I said it. And as it was said in the abstract, it is a joint work with three people, Gilles Bonnet, Anna Gusakova, and Christoph Telly. Okay, and I will speak about the result in RD, Euclidean space, but let me start with the plane and to give you some motivation and actually to explain all ideas. It will be enough to be in R2. A very famous and classical question in the integral geometry is due to Sylvester in 1964. He asked the following question. Assume that we have a convex figure, K on the plane, and I assume that it has non-empty interior. And it is convex also. Convex. In other words, it's convex body in the plane, convex K. And we choose independently and uniformly 4 points inside K. So x1, x2, x3, and x4 are IID uniformly distributed inside K. And Sylvester asked, what is the probability that the convex hull of these 4 points, x1, x2, x3, x4, form is a triangle? So what is the probability? Of course, it's a little bit incorrect because, of course, this probability depends on the shape of K, and so it must vary in some range. And Blaschke in 1917, he answered this question in the following sense. Okay, let us denote it by alpha, this probability. He proved that the following inequality holds. 35/12 pi square is at most this probability and at most 1/3. And moreover, this lower bound and upper bound, they are optimal. In the following case, this here equality holds if and only if it is ellipse, and here if it is triangle. Let us note that this probability is invariant with respect to affine transformations. So of course, if it holds for one ellipse, it automatically holds for all ellipses, and the same here, particularly for the disk and for the regular triangle. Okay, and let me make, so I have exactly 60 minutes, yes? Okay. Let me make the following observation about this probability. If you would like to calculate it, to transform it, alpha, what it is? Actually, it holds if and only if one point lies inside the convex hull of other 3 points. And there are 4 cases. First one is when x1 belongs to the convex hull of x4. Convex hull of x1, x2, x3. And also we must add other 3 cases, but since the points are identically distributed, all other probabilities are the same, so we have just to multiply it by 4. Okay, And to calculate this probability, actually, let us for the moment assume that x1, x2, x3 are fixed. We make condition on this point, and then take average. So it's a kind of formula of full probability. So, and if these points are fixed, then the probability that uniformly distributed point belongs to some set, it is just geometric probability. So it is the ratio of the area of the set divided by the area of all figure k. So it is area of convex hull x1, x2, x3 divided by the area of k. And of course, since they are random, we have to take expectation here, and also this coefficient 4. Okay, so we have the representation of this probability in terms of this quantity. And immediately we get that this result due to Blaschke is equivalent to the following. So to get this probability, we have to divide by 4, alpha by 4. So we have 35 over 48 pi square. At most, this ratio, expected area of convex hull of 3 points, and over the area of k, and at most 1 over 12. Of course, it is also due to Blaschke because it is equivalent. Okay, and it is very classical result, and it has partially it has a generalization to any dimension, And concerning this bound, it was obtained by Grömer, and now it is known as Blaschke Grömer inequality. And of course, I have to say that for dimension d, we take some convex body k, take d plus 1 point uniformly distributed and independently inside k, take the convex hull, which is a random simplex, take the volume of this random simplex, expected volume, and normalize by the volume of k. It is what we have in d dimension. And Grömer also obtains that the lower bound for this ratio for dimension d achieves for ellipsoids. And what is interesting that concerning the upper bound, since in the plane it achieves for the triangles, it is natural to suggest that for d greater than 2, this also true for this upper bound achieves for simplexes. And I think it's true, but nobody can prove it, even for dimension 3. So it is famous simplex conjecture. That in dimension d, in any dimension d, this ratio is bounded from above by this quantity for simplexes. And it is a very famous conjecture. For example, it is very important in asymptotic geometry analysis. So this conjecture would imply the famous hyperplane conjecture, which, roughly speaking, says that there exists an absolute constant which does not depend even on dimension, such that if you, in any dimension ID, if we take for simplicity, if you take a symmetric body centered in the origin, if you take a symmetric body K of volume 1, then there exists a section by the hyperplane through the origin such that the area of the section is greater than C. For any dimension D, and C does not depend on D. It is also very important conjecture in asymptotic geometry analysis, which would be true if this conjecture is true. Okay, so in dimension D, this is still open. Okay, and what is my aim in my talk? My aim is to consider the following question: what happens if we consider not the area but consider the perimeter in this problem? Okay, maybe I write here. So in this case we have the following quantity: the expected perimeter of the convex hull of x1, x2, x3, normalized, of course not by the area, but by the perimeter of K. And we would like here to found optimal lower and upper bounds for this quantity. And of course, a very simple observation about the expected perimeter that, okay, this guy is the sum of the lengths of the edges. Yes, so the first edge is x1 minus x2, and other two guys actually are the same, yes, because they have the same expectation. So it is just three expected mean distance between 2 points. So actually in this setup we have not 3 points, but we have 2 points. And the equivalent problem is to consider, okay, and let us denote this by delta of K. So delta of K is the mean distance between 2 points independently and uniformly chosen inside K. So this problem about the perimeter, it is equivalent to the problem of finding the lower and upper bounds for the delta of K over perimeter of K. And we will find the optimal bounds in the plane and in arbitrary dimension D. But before doing this, let me make some historical remarks. Okay, great. About delta K. Actually, it is very popular quantity in stochastic geometry or in integral geometry, but not too much known about it. It is explicitly calculated for several examples, and most of these examples are on the plane. And very few examples are known in upper dimension. I will tell you about it. And also little known about the bounds for this delta. And I will tell about this also. Okay, the first result about delta of K was due to Crofton in 1885. He calculated delta of K for the regular triangle. Delta of a regular triangle. By the way, here I said that this quantity, this probability or this quantity, it is invariant with respect to the affine transformation. Of course, it is not true for this guy. It is not true neither for delta of K, neither for the perimeter, and neither for their ratio. So it is different for regular triangle and non-regular triangle. So Crofton obtained this for regular triangle, and it is just A. A, it is the side of the regular triangle. And 1/5 plus 2 over, let me check, sorry. 3/20 log 3, yes. 3/20 log 3. And in 1951, Gauche considered a square, again with the side A, and the mid distance between 2 points in the square, it is A/15, square root of 2 plus 2 plus log 5, 1 plus square root of 2. It is outside the log. A couple of more examples.
Dmitry, could you write a little bit larger?
Larger? Okay. Okay.
For the Zoom, it
Okay. Thanks for telling. Okay, in 1964, I think it was done much earlier for the disk, because it's even easier than for the regular triangle. But the first reference we found, it is this reference. It is Fairthorne. Larger, okay. Fairthorne. He considered a disk of radius r, and it is just r, the radius, multiplied by 184 over 35 pi. Okay, later in 1985, Shen considered arbitrary triangle, ellipse, and also parallelogram, but the formulas are very complicated. Not very recently, in 2012, Armenian mathematician Aharonyan he considered a regular hexagon. And in 2014, Basil, he considered regular n-gon, and he obtained a very complicated formula for the distribution function of this distance, x1 minus x2. And using this complicated formula, he managed to obtain a formula for delta of n-gon only when n is 3. Only when n is 3. And when we prepared the first version of our preprint, it was about 1 year ago, we cited this paper, and as I said, we mentioned that from this formula it was derived the formula for delta only in case when n is 3. And after that, it doesn't work? Okay. After that, okay, maybe it's better. Oh, neither. After that, I think he read our paper, and in January of this year, he sent us a letter which with the reference to his preprint of 2021. And in this preprint, he obtained the formula for delta for any regular n-gon. And also not only for the average, but for any moment. The formula for any moment of this quantity for the regular n-gon. And also he noted that based on his formulas, which I believe are correct, he mentioned that this formula actually is incorrect by Agharonyan. Okay, and that is concerning the plane case. As I said, little known in higher dimension. Actually only one setup is known in 1971. Miles considered a unit ball, and he obtained a formula for the delta of BD, where BD a unit ball. And the formula, actually he obtained much more general result. He considered several points, k plus 1 points, where k is not greater than d. So the convex hull is a random simplex, and he considered a k-dimensional volume of this simplex. So when k is 2, it's just the length, our length. So from his general result, we have the following formula. Delta of BD, it is the following thing: 2 to the power 2d plus 2d gamma square of d plus 1 over 2, and divided by here d plus 1 p and 2d plus 1 double factorial. Okay, so we have this explicit formula. And also if we consider not the unit ball but the unit cube, then delta of the unit cube, it is so-called box integral. Of course, this quantity, just by definition, by the definition, it is a double integral over k. Yes. So this quantity can be expressed as the double integral over RD or over this cube. But the question is how to simplify this integral, yes? And the only, of course, for d equals 1, it's just a segment, it is known. For d equals 2, it was by gauge, it's square. And also it is known for d equals 3. It is well-known Robin's constant. So here, so it is for d equals 3. Box integral for d equals 3. He calculated it. Actually, he expressed it very similar to this. It is just a sum of 3 fractions, and each fraction is expressed using square roots of 2 and 3, logs, and also pi. So elementary expression. But when d is greater than 3, there is no formula for this box integral. No formula, which is interesting because if we have this formula for 2 and 3, so there is a hope that the same formula must be correct in using only square roots, pi and logarithm. The same formula must be correct for higher dimensions. Okay, that is actually literally all examples where the explicit formula for delta is known. And now let me tell you something about the bounds. The bounds for this quantity. Actually, there are few bounds. The first one is classical, again due to Blaschke from the same paper, 1917. He estimated this quantity in terms of the volume of K. No, actually, he considered dimension 2, and he considered delta of K normalized by the area, but of course it has degree 1 and area has degree 2, so we have to take square root of the area. Square root of the area of K. And he proved that it is at least 128 over 45 pi, and here to the power 3 over 2. And it is exactly the same quantity if you take the unit disk. No, not unit, arbitrary disk here. It is so the equality holds if and only if it is disk. It is disk. And now a question to you. What about the upper bound?
Infinite.
Yeah, exactly. Because
Divide by perimeter or diameter or not by the area.
yeah, thank you. Yeah, because simple example, if you consider rectangle, here 1 and here epsilon, when epsilon goes to 0, this quantity goes to infinity, of course. Okay, and later this result was generalized for any dimension, for dimension d by Pfeffer. Of course, here we have to normalize by the delta of K, normalized by the volume of K to the power of 1 over d. And again, the lower bound is the same quantity for the ball. Okay, and maybe the last estimate for this quantity, it is recently it was obtained by Burgstahler and Pilix. Hammer. They considered this quantity delta of K normalized by the diameter of K, and they consider only upper bound. It is some constant CD. It is explicit. They wrote explicit constant in terms of gamma function, something like this one. But apparently this constant is not optimal. Not optimal. Just some bound. Non-optimal. Later I will tell you.
So it does depend on dimension?
Depends. CD. Yeah. And this constant is not optimal. Later I will tell you my conjecture what is optimal here. And no lower bounds. And later I will tell you what is the lower bound here. It will follow from our result. Okay, and now maybe it's time to formulate our main result. Maybe here.
Well, how does this constant behave? Well, it's always less than 1, right?
Yes, yes. It is, yeah. On the plane, it is something like.
I mean, asymptotically in dimension, does it kind of go to 0 or what? Stays near 1 or what? It looks like it should go to 1 when dimension grows, right?
You mean the right constant, the optimal constant? No.
Just compute for the ball, yeah?
And
Most parts of the ball are kind of diameter.
but for the ball, I doubt that it goes to 1.
No, it doesn't.
No, and actually you are right. It is the optimal one is for the ball. It is my conjecture, but
Maybe it's not. It doesn't go to the average. Maybe it doesn't go.
Okay, and now I think I don't need this.
And excuse me.
Yes.
Another question. What about second momenta? They should be something much easier to handle, I think.
Yeah.
Yes, they kind of they might depend only on inertia ellipsoid or something like this. Is it true?
Actually, we didn't try because it's not so popular, the second moment. Yeah, you're right. It is much easier calculated. Like.
Oh, I mean, you get a bound for the second moment, and just like square root of that will be maybe not so bad bound for upper bound for this.
Yeah, I think for the second moment it is easy to prove that the ball is the optimal bound, but.
Yeah, of course, the square root of that will not be optimal, but something.
Yeah, you're right. Maybe we should try, or maybe ask some student to do for the second moment. Yes, of course it must be easier. Yes. Okay, and concerning our result, first let me formulate it for the plane, and later, a little bit later, for any dimension. For the plane, we prove that the following bounds hold. It is not greater than 1/6, and it is greater than 7/6t. And both bounds are optimal. Optimal, what do I mean? Why they are optimal? Because, for example, here, if we consider the following figure, triangle with two equal edges, this edge is 1 and this is epsilon. So when epsilon goes to 0, then the quantity, this ratio for this triangle goes to this. So asymptotically it is optimal. So we can found a figure for which this ratio is arbitrarily close to this bound. And concerning this upper bound, here the example is rectangle. If you consider the rectangle with h1 and the second h is epsilon, again when epsilon goes to 0, this ratio goes to 1/6.
So you normalize by diameter or perimeter?
Perimeter, yes. Perimeter. And essentially, the example where this ratio bound achieves here, the upper bound achieves, actually it is the segment. For the segment, we have exactly 1/6. But as I said at the beginning, we consider figures with non-empty interior. So in the class of figures with non-empty interior, these bounds are non-achievable, but asymptotically optimal. If we consider convex compacts, which might have empty interior, then this bound is achievable on the edge, on the segment. But this bound is not achievable even in the class of compacts. In some sense, this bound is achievable on the segment with non-uniform measure, but with measure which behave like this.
Do you consider also possibility of having a non-uniform distribution in the plane for the points?
Like something like Gaussian, for example, yeah? No. It didn't. But it makes sense, yes, sure. And actually what is interesting, these two examples show us that this quantity is non-monotone. It is not true that if k is inside L, then it's not true that delta of k is not greater than delta of L. So if you consider these two examples, the first one, L is our triangle, and k is something like this rectangle. They have almost the same, this edge, and they have almost the same perimeter. Not almost the same, but very close, because this height is very, very low. So they have almost the same perimeter, but this ratio for the rectangle is much larger than the ratio for the triangle. And since the perimeter is almost the same, it follows that delta for this rectangle is larger than delta for triangle. So this is example that delta of k is non-monotone, which is interesting in my opinion, because intuitively, for me, for example, from the beginning, I thought that it must be monotone. And by the way, this 1/6 is 10/60. So this upper and lower bounds actually close enough. So from this we can conclude that perimeter it's good approximation for this delta with factor 17/120 multiplied by perimeter and plus minus error not greater than 17%. So in some sense, this perimeter of k is a good estimator for this quantity delta. It follows from this. Okay, what about high dimension? But before formulating result, let me show you one formula on the plane. On the plane, it is so-called Cauchy formula for the perimeter of the k. Perimeter of the k, it is, I think you all know this very well, it is pi multiplied by the integral over the unit circle. Projection, the length of the projection of k into the unit vector u, and then we must integrate over all unit vectors, mu du. So we take our convex figure, take some direction u, project our figure here, take the length of the projection, and integrate over all directions. In some sense, it is mean width. So width with respect to this u is this one width, and then we take average width. So it says that on the plane, the perimeter of k, it is up to the factor pi, it is the mean width. And why I'm telling you this? Because here on the plane we normalized our mean distance by the perimeter. And in higher dimension, perimeter actually it is a surface area, and it has dimension d minus 1. So we can't normalize by this. And we have to normalize by something which has also dimension 1, and actually it is a mean width. Maybe some of you know what is intrinsic volume. So the most natural normalization.
Mass integral.
Yes,
Pure mass integral.
yes. But normalizing something different. Yes, and so actually first square mass integral or intrinsic volume, it is actually the mean width. So to have a correct formulation, we have to normalize in dimension d, d. We have take our quantity. Now K is a d-dimensional body. And normalize by the first intrinsic volume. The first intrinsic volume, as I said, it can be defined exactly like here, but only we have to integrate over the d-1 dimensional sphere. We again have to take the width with respect to some direction and integrate over all directions from the unit sphere. And also we have to take some normalization to obtain the first intrinsic volume. This normalization is taken so that, for example, if you take two-dimensional disk, unit disk, it has on the plane it has a width, average width 2. Yes, because if we project on any dimension or any direction, the width will be 2. But if you take two-dimensional disk and put it inside R3, then of course its average width will be less than 2, because we can project over other directions. With respect to the directions, the width is less than 2. But if we normalize properly this mean width, then it will not depend on the dimension of the surrounding space. And it is the first intrinsic volume. So it is the right quantity to normalize. And for this, we obtain the following bounds, also optimal. The upper bound actually the same, but perimeter it is doubled with 1. So here we have 3 for any dimension. So the upper bound optimal and even does not depend on the dimension. The lower bound depends on the dimension, and it is the following. It is 3d plus 1 over 2d plus 1 and 2d plus 1. And again, both bounds are optimal, and the extremizer for this guy is again the segment. Actually, it is parallelepiped with one edge 1, and all other edges are epsilon. And extremizer for this guy, it is like this one, but here we have to take, okay, in R3, for example, here we take here epsilon, and here 1. And so we have the following polytope.
Dmitry, maybe a little bit larger for our Zoom.
Yeah, sure. In dimension 3, we have to, here we take -1, 1, and here we take epsilon, and here we take epsilon. And we take convex hull of these 4 points. So we have a simplex. This edge is large enough, and this are epsilon. And this is extremizer for the lower bound. When epsilon goes to 0, this ratio for this simplex goes to this bound. So again, these bounds are asymptotically optimal. And okay, now about corollary from this. From this, we immediately obtain the corollary for the lower bound for this quantity, which this guy is considered. It is known that V1 of k is at least the diameter of k. For example, for those who knows, it follows from the monotonity of the first intrinsic volume. Because if you have a body, and here is a segment which realizes this diameter, then the first intrinsic volume of the body k is at least the first intrinsic body of this segment. And the first intrinsic volume of the segment is the length, which is the diameter. Since the segment lies inside k, then diameter is at most V1 of k. And so from this we have this inequality, but for the delta normalized by the diameter. And the question is whether it is optimal or not. And it is very easy to see that it is optimal because this extremizer, which realizes asymptotically this bound, actually the same works for him for this quantity, because asymptotically on this simplex, when epsilon goes to 0, then the diameter and first intrinsic volume of k actually the same asymptotically. So immediately we have that this optimal bound for the delta of k normalized by the diameter. And what about the upper bound? And we have a conjecture, me and Anna Gusakova, that it is maximum when the body is a ball. For example, a unit ball, then we have delta of BD, which was calculated by Miles. This formula, it was written here. And the diameter of the unit ball is 2. So we believe that the following estimation holds, and also it is optimal. Of course, if you prove that it holds, it automatically will be optimal because this guy is for the unit ball. And actually, we didn't manage to prove it even on the plane. So it is open even for d equals 2.
So what is the question? The average length of segment divided by the diameter?
Yes. Yes, the lower bound automatically follows from this result. It is the same. Because on the extremizers, V1 and diameter are the same. And the upper bound is open, even on the plane. Okay, and since I have 8 minutes, let me give you briefly the idea of the proof of this one. I will give you the idea of the proof on the plane, and for high dimension it is similar. Actually, we are going to use this Cauchy formula. If you put here the segment, so expected x1 minus x2. Then the length of the segment, it is semi-perimeter of the segment, yes? So by this Cauchy formula, we have expected not pi, but pi over 2, because it is half of the perimeter it length. Then the integral over S1 length it is just the norm of the difference. Projection x1 to u minus x2 to u. Okay, mu du. And now let us fix u and consider this, and then we by the Fubini put expectation here and consider this expression under the integral. Expected x1 to u projected into u minus x2 projected into u. We have the following picture. We have the following picture. Let us u be horizontal u. So we project our body here. That is x1, x2. And we project it here. Let it be t1, this point, and this point be t2, t1, t2. So we have since our measure is uniform over our body, it is just double integral. For example, when we take expectation with respect to x1, we have to integrate its first coordinate, which is t1, over this segment, and then second over this section. So and the same with the second point. So we have first double integral over k projected to u, and also k projected to u. It is for the first coordinates of our points. And then our projections, it is just t1 minus t2, this one. So t1 minus t2, and then we must integrate for arbitrary point. We must first of all first coordinate integrate over this segment, and second integral integrate over this. So to take the length of this interval. And for point t, this coordinate t, let us denote the length of this section by g of t. So it will be g of t1, g of t2, and dt1, dt2. And since our measure is not Lebesgue, it is normalized measure, we have also to normalize 1 over volume of k square. Okay, and maybe two more words. Let us make some transformation which put this interval into the interval 0, 1. After these transformations, we obtain some factor, the length of k over u, and multiply by the integral 0, 1, 0, 1, some transformed g, which I denote by g tilde, or maybe f of t1, f of t2, d t1, and d t2. Okay, and actually we have this quantity and
the difference of t1 and t2.
Sorry? Yes, sorry, thanks. And also the difference, yes, t1 minus t2. dt1, dt2. And let us denote this double integral. It is just as functional of t. It is just projection k into u and multiply by e of f. And somehow we would like to maximize and minimize I of f over the class of functions f. And what about the class of function f? Okay. The class of function f is the following. Let me remind that f we take from G, f is transformation over G, and G is a section function of a convex figure. So f possesses the following properties. First of all, f of course is not zero, and support of f is 0, 1. Second one, f is concave on its support. And this is just on the plane. You can see this. It is just, it's not difficult to prove. But in dimension 2, it's so-called Brun concave principle. And if we have dimension d, then not f, but f to the power d 1 over d minus 1 is concave. It's so-called Brun principle. And the third one, integral from 0 to 1 f is 1. And we would like to, in the class of this function, we would like to find the maximum and the minimum of this functional. And actually, technically, it's not easy, very easy, but actually the answer is the following. The minimizer in this class has the following graph 0, 1, and here 2, the point 2. It is the minimizer. And the maximizer, and this minimizer, of course, gives us this answer. And the maximizer, it is just constant function, which gives us this extremizer, the upper bound. And it is on the plane, the maximizer, because on the plane we have that f is concave. But for any dimension, we have to take this triangle and take the d minus 1 power of this triangle, and this will give us the answer for any dimension. So we take triangle which is for the plane and put it to the power d minus 1. So f is in this class. And the extremizer will be the power of this triangle, normalized property. That is why we have not this guy, but this guy in any dimension. Okay, I think I have to stop here. Thank you for your attention.
So, are there any questions or comments?
I could suggest to look at the more general distributions in the plane and maybe come something like eigenvalues of random matrices, for instance. Like you take Ginebra, they will also be not independent. They are have some. So anyway, it could be quite interesting.
Yeah, we can discuss it later. Yeah, it would be fine.
Concerning that question about average distance over the diameter on the plane.
Yes.
Conjecture that the optimum is around this graph.
Yes.
Did you test it against Rayleigh triangle?
Yeah, we simulated. It was our conjectures. Maybe Rayleigh triangle is larger, but not. Yeah, we checked it.
It looks like, well, from intuitively, it looks like.
No, it is a good guess, but it didn't work. But actually, we would be happy. The answer would be Rayleigh, not so trivial. But unfortunately, simulation showed that no.
So, did you
We calculated the integrals. Yeah, it's not difficult.
I mean, does it make sense to choose?
You mean Monte Carlo method? No, we just calculated the integral. Yeah.